say anything ugly about Ethan and Virginia. That's the first thing they're going to hear on the video. They're like, oh, great, so they've been talking about us for an hour. That's kind of funny. All right, so we're going to talk first about how, and I want to write this heading and I want you to tell me what this means. F prime of A might fail to exist. What does that mean?
Is it kind of like the limits where if the left and the right aren't equal, then the overall is?
Oh, she's getting ahead of me. I just want you to explain the notation. What is F prime of A? So basically this is saying how. So the title is differentiability. So we're going to look at when the derivative is there and when it's not there. And there are actually 4 specific cases you want to know. We'll start with number 1, as it's listed in your book, and that is a corner. At a corner. Number 27, which we did a few minutes ago, looks like a what?
Upside down.
An upside down absolute value graph. The absolute value graph is your classic example of a corner. I believe in chapter 2 we discussed whether or not the limit exists at the bottom of that V, didn't we?
Yes, it does.
Okay, all right. So let's rewind to the beginning of today's discussion. When does the limit exist at a point?
When the two trains meet.
Oh my God. Okay, I'm going to turn my back, and Nelson's going to pop him in the neck for that, because he said when the 2 trains meet. Okay. when does the limit exist? When the left and right hand limits are equal. When the trains end up at the same station, like he says. Yes? Okay, apparently that meant something to him because he's stuck with it. All right? But what had to be true for it to exist at the point? They had to be equal, right? Are these 2 limits equal? Are the 2 derivatives equal?
No.
What's a derivative?
The slope.
It's the slope, which is a limit, right? Okay, so if you have, what you're going to get from these 4 rules is that if there is a sudden change in the derivative at a point, the derivative does not exist there. Got it?
Wait, what?
If there is a sudden change in the derivative. Because when we look at this picture of this absolute value sketch that I just threw up here floating in space, as I move on the left side, pointing in the standard position up, what can we say about the slope on the left side?
-1.
Right? -1, let's call it -1 if this is the parent graph, right? -1, -1, -1, whoop, something happened right here, right? You see what I'm saying? All right, how about the other side? It would be 1 coming from the other side, right? So clearly 1 does not equal -1. The derivative does not exist at a corner. Got it?
Yes.
Okay? Now, the next thing we talk about is a cusp. And this is what a cusp looks like. No, that's not very pretty. Let me try again. This is a cusp.
So like that inverse sign.
Yeah. Yeah, the inverse sign, but except for the fact that no, not the inverse sign.
The inverse of the sine x over x.
Oh, you're talking about when you put the 1 over x in sine x over x. Okay. But that one kind of squiggles in the middle. This comes literally to a point in the middle. This would be like where you have a rational exponent and you have an even exponent, an even numerator and an odd denominator. You get a graph like this. I call this the cartoon bird graph. All right. How could I take the absolute value graph and turn it into this cusp picture? Bend it, right? So the difference being that the absolute value graph is made up of 2 straight lines, right? And this one is made up of 2 curves that meet at a point. So if they come to a point, again, the same argument could be made for the cusp that we just made for the absolute value, right? Because whatever the rate of change is on the left of this this cusp picture, with it having 2 curves coming in and crashing to a point in the center, if I come to it from the left, what is the derivative? How would you categorize the derivative? Negative, because it's decreasing to that cusp, right? Then what happens? At the cusp, it suddenly decides to increase away from it, what appears to be the same rate, but negative, right?
So an example of that would just be like x squared over x cubed would make a graph like that.
grab your calculators, and I'll pause the video. Let's put a little rule there, because we don't need to describe the first one, right? A corner typically is going to happen either in a piecewise graph like we did for 27, right? Or in an absolute value graph. That's something we're really comfortable with. So here, let's put x to, so what was the one we just graphed? X to the what? 2/3. And why does that make sense after?
X to the 1/3.
Even or odd.
Right, so it's going to be even over odd as my exponent. And that's typically where you're going to see that. Okay? So if you're given a picture that has that characteristic in it, you just know that the derivative does not exist there. The third possibility that we describe is a vertical tangent. And I kind of sneak previewed that for you on the discussion about which of those functions was its own derivative. And we talked about the relationship between x squared and the square root of x. Okay? So anywhere on a graph that I have a vertical tangent, all right, and one that's not obvious right now, but the one that, and they actually have this as the example in the book. I was going to try to think of a different one, but they're using the same one, so we'll run with it. Is the graph we just did, and that is at the center point of this graph, and I will show you analytically how this is true. We have a vertical tangent. Because when you get to the origin on the cube root graph, your rise is some number, but your run is 0. So you're dividing by 0 in your slope.
You gotta be.
So there's a vertical tangent in the center of, and this is x to the 1/3. All right, and then the fourth possibility is at any discontinuity in a function. Now they show you a piecewise picture in your book, but I want you to just make some notes about whatever makes sense in what we're about to talk about. Okay? If you, and I know Zach's having this experience because he was talking about it the other day, if you had a couple of Algebra 1 kids that you were helping with their homework, and they were doing a lesson on slope, which ironically enough, my Algebra 1 class is doing today. But if you were going to explain to them exactly what slope is, what would you say about it? It's rise over run.
It's the change.
The direction.
If it's the rise over run, that makes it a ratio, doesn't it? It's a ratio of what to what? What's another way to talk about rise? At how fast the y is changing compared to, on that same interval, how fast x is changing, right? Okay? In other words, slope is a description of a characteristic of the function itself, right? So when you're trying to get all this straight in 3-2, revert to lines and think about what slope tells you about a line. If I say that a line has a slope of 7, what do you know? That it's, because it's a line, it's doing the same thing everywhere. What's it doing? It's increasing. Would it be pretty steep or pretty flat? Pretty steep, right? Because even 7's a big number as slopes go. All right? So doesn't it make sense that if there's a hiccup somewhere in the function, I can't talk about the slope where the function doesn't exist? So I think the best way to remember this one is no function at x equals a means no derivative. So no f prime at x equals a. And we could write that more succinctly as no f prime at a. So if the function doesn't exist at a, I can't even talk about the slope. And that becomes really important. Speaking of discontinuities and strangenesses, and I think this was on the actual test, not the retest. Remember the one where you had to determine what discontinuities exist for a function and tell me what kind and whether or not they were removable? I had a couple people tell me that there was both a whole and a vertical asymptote at an x value.
Slam.
Is that possible?
Yeah.
No,
Only in certain cases.
not so much. Only what? Don't forget, I got Nelson behind you.
He's a nice guy there.
Nothing. Oh, is that my weakness in choosing Nelson as my hitman, so to speak?
What's his weakness?
His niceness.
Yeah, he is really nice.
You brought that up, which is why I said never mind. Why am I even trying? Why? Okay. Y'all, if your book is open, and if it's not, don't worry about it. But I just want you to just share in what I find a bit humorous and sort of strangely ironic. Look at the title in red on page 110. Please read it aloud to me when you see it. Okay, differentiability implies local linearity. Okay, and then, well, I guess that wouldn't. I guess never mind. It's not going to be quite as funny to y'all, so never mind. All right, differentiability. I'll explain it when I get to it. It's not going to be as funny till I explain that theorem to you. All right, differentiability implies, not of, local linearity. That is a very important thing to absorb the impact on. Okay, well, to be able to absorb that, we have to understand each word in that statement. What is differentiability again? Whether or not there is a derivative. Okay, so if I say that something is differentiable, what am I saying about it? It has whatever it is, whether it's an interval or a function, whatever. That thing that we're talking about has a derivative, yes? This statement tells us that if we know that, it implies local linearity. What do we mean by local linearity?
It will be a line.
Yes, sir.
Or it has characteristics of a line.
Okay, well, now look back at the 4 exceptions to where a derivative exists, and let's look at the first possibility. On what part of the picture of the absolute value graph is that graph not only locally linear, it is actually explicitly linear? Both sides. In other words, everywhere but at its center, right? So the derivative exists on both sides because if I know what the equation of that thing is, I know what the slope of each side is, right? So I know that it exists if I am dealing with something that is in fact linear, right? When it made that sharp turn to make that corner, no, it's not. I don't have a derivative there. You with me? Okay, so if I did a piecewise description of the derivative there, it would look like 27, right? But on an actual absolute value graph, one would be positive and one would be negative, whatever my A was, right? Okay? So, local linearity is like, if you take the sine graph, and I think we did this, and if we didn't, we'll pause and do it, and I might have you do it since my software's not playing nice together today. Did we take the sine graph last year and zoom in on it and zoom in on it and zoom in on it?
Yeah.
What did we see finally?
It's a line.
Well, the sine graph is an oscillating function, clearly, yes? But if we zoom in at the origin, it's a line. Not only is it a line, in fact, we talked about this in the context of sin x over x, didn't we? If we zoom in on it far enough, what line does it look like? Y equals x, right? Okay? So that's what locally linear means. If I can take a function and zoom in far enough on it that it looks like a line, it has local linearity. So even though you wouldn't want to take the time on a function to do that in a lot of places, because that's a lot of zooming, right? But you can imagine that any function, if you zoomed in far enough, I could make any curve that's a nice, smooth, well-behaved curve. I could find a spot where it looks like a line. If I can make sine look like a line, I could surely make a parabola look like a line if I zoomed in far enough. Does that make sense? Okay. What does that relate to? How does that relate to tangent lines?
Because if it's
What is a tangent line?
a line,
It's a line that intersects a function at a point of tangency, right? And what does it tell me about the function? It tells me everything where? At the point of tangency, right? But the further away from that point, what happens? But if I took that line, if I could move the line from point to point, imagine that I take that same image in my mind where I have a curve with a tangent line and I keep sliding the line along the curve, there would be a tangent line everywhere, right? Everywhere I can put a tangent line, that mimics what the function's doing, I have differentiability. So that's what this is saying, okay? So locally linear, or local linearity, to say exactly what they said, and you will see these, this term used in different contexts, so it will be in different forms. But local linearity simply means that a tangent line exists for that point. And if you think about it in this paraphrased definition, what your book tells you, a good way to think of differentiable functions is that they are locally linear. That is, a function that is differentiable at A closely resembles its own tangent line very close to A. But if you think about it from a standpoint of, can I get a tangent line in the picture that looks like what the function is doing at that point? If you go back to your absolute value picture, works perfectly everywhere but at the V, right? How about the cusp picture? I could get tangent lines anywhere on the curve except where it goes to a point. You see what I'm saying? How about on a vertical tangent, what would be wrong there?
Tangent line's still vertical.
That's right, the slope is undefined, so I can't write a tangent line there, right? I can't write the equation of a tangent line. Does that make sense? Okay.
Tangent line.
Okay. I'm going to talk to you about page 111. I'm not going to make a big deal about it because I feel like this is becoming less and less of a thing that's talked about because of technology's use in this realm. Numerical derivatives on a calculator. If you ask your calculator to do anything, and the wonderful machines that I have now asked to be ordered, and some of you already have, those InspireCasts, they are in essence computers in your hand instead of just calculators now. They're gonna, the more accurate they can make technology, the more information they can get into a little chip, the more accurately they will do what they do. But what they do is, everything they do is with the estimation approach, okay? And that's what they're talking about on page 111. Numerical derivatives on your calculator use the symmetric difference quotient. What is the difference quotient?
The
That's chapter 2.
the limit is
No. You're in the right part of your brain, but it's not a limit.
it's the
What is a difference quotient? What is the difference quotient?
It is that one.
It's what? That's right. It's f of x plus h minus f of x over h, right? Because it was really x plus h minus x. Yes? That is the difference quotient. If I put the limit in front of it, that's not the difference quotient. A limit, or the instantaneous rate of change, is the limit of the difference quotient. That's why y'all screwed that up on that quiz. Because you were asked for the difference quotient and you were giving me the instantaneous rate of change. So what does symmetric mean? Okay, so listen to the definition, and I'm not even going to have you write this down because I just don't think it's that important. You might have a few problems, but if you do, come back and look, and I'll answer questions on Monday if you have them. The symmetric difference quotient is f of a plus h minus f of a minus h over 2h. Do you hear the symmetry there? So now we're not just doing f of x plus h minus f of x. Now we're doing f of x plus h minus f of x minus h. Okay? Does that make sense? And then, so if I'm doing that, then now, instead of using 2 points that are arbitrarily close to some chosen value, what does that mean? I'm going to find the value I'm interested in, and then I'm going to look the same distance on both sides apart to use as an approximator of the slope. Does that make sense? So I want to squeeze it from both sides, in essence, and that's what the symmetric difference quotient does.
Isn't that kind of the same thing we did on that one homework problem?
What'll happen is you'll learn so much calculus by the time you take the calculus exam that you'll forget that you've got to kind of revert almost to Algebra 1 thinking when you're in certain situations where you don't have a function and all you have is a table of data or something. But we'll talk a lot more about that too. But yeah, that's a good point.
Isn't that always going to give you like 0 on top? If you do that?
No, because f of a plus h, let's say a was 3. And I told you we're going to use, for our h, we're going to use 0.01. 3 plus h would then be, x plus h then would be 3.01, right? What would 3 minus 0.01 be? it'd be
2.9.
2.99. You see what I'm saying? So it's going to be really close to zero, but you're right. That's what it does. It uses an approximating algorithm that comes from that definition. All right. This is the thing that I find kind of ironic, that they have this statement over on one page and then you get this theorem. All right, but we have another title, and I'm not even going to write the title because the title of the theorem is the same thing as the title of the section. And this is very important. And this is Theorem 1 in Chapter 3 in this book. It's not Theorem 1 in other textbooks, so don't say, well, by Theorem 1. Differentiability. And if you've been paying attention this morning, and I do realize it's Friday morning, you may not be able to recall it the way I want you to. Differentiability implies continuity. Now that's the title of the theorem, but we're not even going to write what the theorem says because that's what the theorem says. And if you've been paying attention, now my discussion, and I wanted all this all on one screen to make the point, differentiability implies local linearity. Well, if we've just determined that we have derivatives everywhere except at a corner, cusp, vertical tangent, or any point of discontinuity, right? So, and what did we say, or what did I point out to you in the context of that in terms of talking about what slope is?
Say what?
Yes.
What did we say about what slope is just a few minutes ago so that this makes perfect sense? What is slope?
Change in y.
Right? So it's an attribute of the function. And what does that have to do with discontinuities? You're killing me. Well, at discontinuities, we don't have a function. And if we don't have a function, we can't describe its attributes, right? So, like, if I ask you to describe Haney's invisible friend, you'd have a problem, wouldn't you? You see the problem? If it's not there, I can't describe it. Are you with me? So, yeah, that's what I'm saying. So then why does it make sense that if I tell you something has a derivative, it's continuous at that point? Yeah. If I say, well, the slope is 4, well, then there's the slope of something, right? I can't say that I have a slope at 4 or of 4 at some point if the function doesn't exist there to have a slope. Doesn't that make sense? Okay. So, and I want you to write this as at a point, because I want you to think big picture about this theorem. That's mostly how we're going to use it. But everything we talk about in detail like this, you want to think about it in the context of point by point by point. And you could build the same argument for a whole function. All right, I think I already know that this is a pointless question, but maybe somebody will impress me. Talk to me about the IVT.
What?
That's whenever it has the.
Okay, stop. Becca's talking. Go, Becca.
Whenever you drew the graph, it was like the two pieces, and then there was one between them, and you drew the line over.
That's right.
That's the one.
That's okay. You got everybody
So I
going.
look at the world order.
No.
Word.
Whose word was it?
Savannah.
Go, Savannah. Tell us about the intermediate value theorem.
So the function is continuous at an interval from a to b, then every point in between those two exists on the function.
Okay. That's almost perfect. Now,
Look at what it says.
no one? Maybe if I sort of sketch the picture back up here, maybe, God forbid, you could flip back in your notes to the original picture. So we have some sort of a curve, and it's on an interval from A to B. So this is A, F of A, and the other endpoint is B, F of B. Yes? Now, what we said, and Savannah sort of said this, but her language wasn't perfect, and I was hoping someone would go, oh yeah, this is what it said. All right? It says that if you have a closed interval that is continuous, then by the intermediate value theorem, that between, if I choose a value between A and B, then I know that its y value has to be what? between f of a and f of b, right? So it's specifically talking about the output of the function there, right? Well, why did I bring that up? Well, because theorem 2 in your book
No.
is the IVT for derivatives. Okay. And we're going to write this one out. Obviously, we need to. If A and B are any 2 points in an interval on which f is differentiable.
Is there any way to abbreviate differential?
You can abbreviate it for your own reference to just DIFF if you want to, and I will do that here. Because notes, and this is another important point about being a college student, if your version of note taking is to write every letter of every word that the person speaking says, you will be in deep, deep trouble in college. So if you need that, you probably should get some sort of recording device, either an app on your phone or something that can do that for you, but you cannot keep up with college professors' lectures. They don't do pauses. They don't slow down so you can write it. They just keep talking. Okay? So you'll get left at the station if you try to do that. So yeah, just abbreviate it so that you'll know what it means later. All right? Then, f prime, what is that? Okay, so my derivative takes on every value between, and I would get you to guess, but I know books are open, so I'll take the fun out of it. F prime of A and F prime of B. So tell me what that means. What is F prime of A? The derivative at A. And what is F prime of B? The derivative at B. Well, let's say that if I tell you that F prime, let's say A is 2 and B is 7. And I say F prime of 2 is -3 and F prime of 7 is 5. Give me a value of the derivative that must take place somewhere on that interval. -1, -1, 0. Why would 0 be an important thing to think about? What does it imply if a function goes from negative to positive and at some point has a slope of 0? That's probably either, the derivative graph would cross the x-axis, but for the function itself, that would tell me that the function either has a peak or a dip there, right? If it transitions between signs. Okay, good deal. All right, examples. And this you will need your books for. Do I need to pause while people... Yeah, that's right. You travel from near and far. From near to far, perhaps. Who drew the picture above the door? Joseph Murphy?
He drew that?
Well, he did it on a computer. He took a graphic design class, but he also originally drew it by hand before he drew it on the computer, and it looked just about the same. But I swear to God, that looks like an exact cartoon version of Joseph Murphy. Jacket and everything. He used to wear that jacket all the time. You know the people that wear like the same jacket all the time? Like you look for the jacket when you're in a crowd to find them? Yeah. Love that kid. He is a great kid. And all that's on tape, recorded for posterity. Maybe I should send him a copy of the video. You ready? All right, look with me at page 114.
What number?
114.
Page 114. Page 114. What a bully. All right. Maybe you could look on with Marquise since now that you've waited until we're talking about it. Number 2, the directions say compare the right hand and left hand derivatives to show that the function is not differentiable at the point P. Find all points where f is not differentiable. All right, so when I look at number 2, why should the place of non-differentiability jump out at me? There is a corner. So you're looking for one of those big four. A corner, a cusp, vertical tangent, and a discontinuity. And that's important because those last two, the corner and cusp, are going to be like the first things you think about. But the other two you're going to have to kind of dig for usually because for some reason they just don't stick quite the same. Now here's the rule on these problems. If it is a line, it being the section of the graph you're looking at, you can tell me the slope directly. You don't actually have to show it with the definition. If it is not a line, you need to compute the slope. Got it? And I will demonstrate that on number 4. But number 2, we have a horizontal line comprising the left side of the graph. We meet at the point, which is a corner, the point P, which is the point 1, 2. To the left of 1, 2, I have a horizontal line, yes? So the left-hand derivative, in fact, let's do it this way. Let's start abbreviating left hand. So let's call it capital L, capital H, derivative equals, what is the derivative? The slope, which is 0 because the line on that side is horizontal, yes? Then we have a right-hand derivative, which you can't like at a glance see it, but it's obviously some positive number. So what does it appear to be? 2. Oh, in fact, they gave us the equation, so we obviously do know that it's 2. Yes? So what would be the closing conclusion to this? Since 0 does not equal 2, the slope does not exist there. Or well, no, what was the exact wording? Oh, not differentiable. So let me take out the slope. In fact, we're gonna write it a smarter way. We're gonna say f prime at what? 1 does not exist. Right? Wouldn't that be the smart way to say that?
Yes.
Okay. You need to write that on every problem. Why? Because you needed to develop the habit of writing your conclusion in a format that is acceptable on the AP exam. And that would be acceptable in the AP exam. All right, let's look at 4. 4 is a bit of a different problem. Why? At a glance?
Because you got like a little curve in there.
Yeah, we have a line and a curve meeting at a point.
It's like a corner cusp.
Let's call it a cusper. No, really, if either side is curved, it's a cusp, okay? So this is a cusp, yes? So we have a cusp, and if you want to, you can make note of what that is. This is a cusp at the point 1, 1. A corpse?
What?
This is not a corpse. I feel like a corpse, but I'm not one. Okay? Okay? Tell me the left-hand derivative
1.
at this point. It is 1, shouts Mackie. Do you concur?
Wait, so do we have to do like what you were saying, since it gives us the equations?
Yeah, it's giving us. So we do.
Like on 1 and 3, where you were talking about.
What do you
like,
mean
the
it gives us the
activities,
equation?
Like of that line, it gives us the equation, so we still have to do the whole.
No, that's what I'm saying. If it's a line, even if they don't give you the equation, if it's a line and you can read the slope off the graph, you can just tell me that's the slope if it's a line. If it's not a line, I want you to show off. All right? So the right-hand derivative, so we're going to also put capital R, capital H, and abbreviate derivative, equals the limit as h approaches 0, 1 over h. I'm pausing because I'm thinking at some point someone might jump in, but never mind. All right, and we are doing 1 over x, so this is 1 over x plus h minus 1 over x. So far, so good? Now what? Okay. Okay.
We're finding the limit because it doesn't obviously give us the
What do I need to know? What do I need to prove that I'm correct in saying that there is no? I need to show that the slopes are not equal, coming from the left and coming from the right. Okay. Okay. And the slope, as we know it right now, is a limit. Yes. This is the definition of the slope. That's what we're doing. Equals the limit as h approaches 0 of 1 over h. And what do I do about the? Need a common denominator. What would the common denominator be? X times x plus h.
Leave it like that. Got it? All right. So what would I have to multiply 1 over x plus h by to get my common denominator? X. So I put an x there minus,
Parentheses, X plus H.
thank you, parentheses, x plus h. Right? So then what happens?
Then can you cancel?
The x minus x goes away, yes? And then the h's take each other out because there's only an h left on the top. But be careful, and I did this on purpose. This is the kind of work y'all do on your test. I just slashed all over it. All right? But what will be very easy to lose in that process is that the top is a -1. So the limit as h approaches 0 of -1 over x times x plus h. Yes?
So then plug on 0 then.
So
X squared.
that's right. We have -1 over x squared. And we don't write the limit because by plugging in 0, we were taking the limit. So I have the slope of 1 over x everywhere. Okay? Now I need to know, in particular for this problem, at x equals 1, what does that give me? -1. So the left-hand derivative was 1, and so we write, since 1 does not equal -1, tell me what to write. F prime at 1 does not exist. And you can put capital D, capital N, capital E as your does not exist.
Woo! Good work.
And that is your intro